Well, everybody has given me a really tough act to follow, okay? In Operaland, they say toy, toy, toy. And I'm grateful to all of you for sticking out the afternoon, right? But I want to talk not just about food security, but how we can engineer better food security. So first off, what is food security? And the way to think about it and to show you is really to show you what it's not. So here's a map from the International Food and Agriculture Organization of 2015. All of these places that have red or brown or pink, the darker the tone, the more people are missing more meals more consistently. So that's food insecurity, okay? When you can't get enough to eat consistently, especially for your children, and most of the people worldwide who miss meals are children, okay, either in utero or on their way up, then you have a problem. So food security is the exact opposite of this. It's no red or brown shades at any magnification in the map, okay, everywhere, around the world, all the time, every day of the week, for everybody. Really simple. Now, if we zoom into the map, even here in Missouri, we have a lot of food insecurity right now, here today. Here's from the Missouri Hunger Atlas that's done in Sandy Raccoon's group of now 3 years ago, and same color coding. So the deeper the shade, the more insecure for food people are. Okay. So now let's scale up the problem, and here is the classic projection. There are a lot of projections about the world's future population, that 9.8 billion people is about the most conservative, okay? So by 2050, we're gonna have about 10 billion people on this planet, okay? And the green line on the top is the predicted demand in terms of total farm output, okay, that those people are gonna need. This orange line is the projected rate based on our current rate of crop and livestock improvement around the world. And then this brown line, the deep doo-doo line, is what it's projected to be in less developed countries, okay? Well, golly, I think everybody can see there's a really big gap, and it's really, really bad. And I want to just point out that it is not just calories, right? It's things like nutritional quality, the taste of the food, the cultural context, and the personal preferences. Raghu and I were talking the other day, and he's a vegetarian, and I'm an obligate carnivore, right? So it's things like that that really matter. Okay. Not only do we have a problem, a sort of moral and ethical problem, but we have a security problem, a diplomatic problem, a global stability problem. Here is a leaf of a coffee plant, okay? Everybody's favorite, or many people's favorite beverage. And that plant has been infected by a disease called coffee rust, okay? As the climate continues to change, the number of pests are going up, the number of pest infestations and poor yields is going up around the world, and we're seeing more and more crop failures for every crop around the world. Of course, it's still erratic. Every time a crop fails, wrong button, then we get a rise in commodity prices. And there have been a number of studies tracing the relationship between changes in commodity prices and civil unrest, okay? And so that's the green line here. The blue line is the changes in food prices. And there have been food riots, even in the last 10 to 15 years around the world, okay? What's the consequence of that? Well, you know, once your crops start failing and you get really unhappy, you move, right? No sensible person would stay put, okay? So coffee rust is a disease that devastated Honduras several years ago. Last fall, 28% of the migrants reaching just Tijuana, okay, were agricultural workers, and most of them are Hondurans. So they've seen this problem before. They're not sticking around to starve, okay? So same way with water and all the other natural resources. So when we think about what we need to do, we often talk in terms of a yield gap. And the gap is in row crops, in tree crops, in vegetables, and also in livestock, okay? This on the left is the potential. People sit around and they calculate what the yield would be based on if everything were perfect, if the weather were perfect, if we had the right genes in the organism, if the management techniques were just hunky-dory, okay? And here is what we get now, okay? So that gap is the yield gap. What's going on? What are the things that we can change? Well, we can certainly change and breed better crops and better livestock. But we're going to find out that it isn't just a matter of throwing a few genes together and stirring the pot, okay? We can certainly, as part of that breeding, make our animals and plants more resistant to disease, less sensitive or maybe more resilient to changes in weather and climate, okay? And more resistant to sort of errors in management, right? If anybody has a garden, you know that certain things can happen when you're not paying attention. Okay. So to close the yield gap, what do we have to do? We have to learn how the organism responds. And the only technical word that they let me use today is phenotype. But it's a really important technical word, okay? The phenotype is what you see or the behavior of the plant and animal. So classic phenotypes of interest to, you know, we should just label these buttons, right? Are things like yield, nutritional quality, disease resistance, I want to come to my own version of that in a little bit, climate resilience, okay? Those are the outputs of this phenotype function. What we put in are the genes, the environment, and the management technique. Those are the inputs. So if we want to make predictions, for example, we want to stir some genes together and predict how well this new organism is going to do in a different environment, we have to understand what the relationship, what this function is. Now, it's a function with many parts. Everybody can see that. It's also nonlinear. And so just for fun, I pasted in some sample gnarly little functions. And like any prediction problem, right, we want to find our place on our function someplace and then read off what the result is going to be. We don't know what the phenotype function is. And it'll probably vary with every organism and every set of phenotypes we want to study. But we have to understand its mathematics so we can do the computations, so we can choose better lines, so we can predict their performance, and so we can even breed more effectively. But there's one thing we already know about that phenotype function. It's not planar. It's not a line, okay? If it were, the current methods would be predicting really well, but they don't. Okay, so when I say we have to learn the phenotype function, and Jack's already told you all about deep learning, so I don't have to, okay, then that's what we have to do. We have to learn that function. So what can we do? We're sitting in a college of engineering. One thing we know how to do is to optimize, right? So there are 4 things we want to optimize here. One is the way we get phenotype information and how much of it and its quality. The plants, how well we predict and how well we breed. So here's my favorite phenotype, which is spotty leaves on corn plants. And that's what I'm out in the summer, every summer doing in the cornfield. For the first optimization for collecting, here is a cheap little drone. It's a DJI Phantom 4. Every farmer, every rancher, every researcher can afford this, okay? Nothing fancy. They're easy to fly, okay? You can fly over your field and you can see what's going on, but when you start to analyze, right, these are the frames in the video recording. And so to figure out what's going on in your field, you first have to paste them together. So Ramana Akhtar with Hadi Aliakbarpour and Felice Bunyak and Palpalaniapan, and some help from me, has written a faster, more accurate algorithm for doing exactly this mosaicing without telemetry data, without GPS, without spots on the ground, purely from the image, okay? So now this kind of work is accessible to everybody once we get it up on a server. So we want to know that function, right? We got to have data so we can flesh it out. We have to collect the data faster, and we have to process the data even better. Okay, next thing. We need to optimize the physiology, okay? So here's some work I did with a colleague of mine, Ann Stapleton. She did a very nice experiment. She got a nonlinear phenotype from different maze lines in response to combined stresses. She said, well, what's the smallest network that can do this? I said, okay. And then after a while, I figured it out. And here's the model, and it does really quite well. Now we have the model, we can use it to ask what-if kinds of questions. How do we tune the parameters? How will we change? How will the response vary? What we really want to do is produce lines like this, right, that have really uniform yield under a very, very wide range of stresses instead of just, peaking at one tiny particular condition, right? So that's what we got to do. We got to optimize the system. Okay. The next thing we have to do is we have to predict the surface, right? If we're going to actually make these predictions, then we have to know what that surface looks like. Okay, well, this we can already do pretty well. Known genotypes, known environment, yep. When we have novel combinations of genes, new varieties, it's harder, especially if we put them, or if we have genotypes in novel environments, it's harder. But here's the hard case, and that's the most important case, because that's the where we're breeding for the future. We know the climate is changing. We have to adapt. If we know those phenotype functions, we'll be able to do these predictions much better. The last thing we have to do is we have to optimize the way we do the breeding, okay? Right now, the breeding cycle, just for maize, takes about 6 to 10 years, and that's before all the regulatory clearances that take another 10 years to introduce the line to the farmer. If we can cut that breeding time, not just by the new molecular methods, but by knowing that phenotypic function, then we could optimize that breeding. So what's that function look like? Well, again, we don't know, but here's the artist's conception. Here we are at the phenotypes we have. Here's where we want to go. We have to stay on that surface, right? If we jump off, we're in organismal outer space, right? So we have to find that surface, and we have to find that path, that green path along the surface, to figure out our breeding strategy. So that's it, okay? We have to somehow ramp up our food production, but do it well and do it sustainably. And I want to just point out that there's lots of pieces of this food sustainability puzzle. I've talked about one today, okay? And a lot of that work is actually going on in this college. So if we're smart, we can do these optimizations, but we need to understand the fundamental mathematics of the phenotypes. And that's going to be fun and exciting and hair pulling. It's a good thing my hair is already white, But here's the thing. Agriculture is Missouri's #1 industry. And here in this state, in this institution, in this system, we have the people and the knowledge and skills and maybe the ability to think a little bit differently to turn that food gap up. So, lots of people to thank, and this is just the top of the plant. There's a whole big root system underneath, and now I think it's time for everybody to take questions. Thank you.